cross section can be written in terms of the transition rate, the flux and the transition rate WFI, the initial flux times the initial target density, and the final state phase space available in this fashion. So, now let us look at it in a little more detail and then write it in a more useful form. First, let us put in the expression that we had gotten for the transition rate WFI. So, 1 V power 4 was already here in d sigma, which is what the cross section that I will denote. Let me write it here. So, cross section, now because we have the phase space factor written as a differential phase space volume element or differential volume elements in the momentum space, we write the cross section as a differential cross section d sigma, and this times the WFI is essentially 2 pi power 4 over V power 4 delta P sum of the initial momenta minus sum of the final momenta. These are the 4 momenta, and then you have the invariant amplitude m square and the flux factor, which is V A minus V B, the relative velocity, the magnitude of that, times 4 times E C E A. Right. So, this is E C V C. Then the final state available d 3 P d over 2 pi power 4 2 E d d 3 P b 2 pi power 3 2 E b. The volume factor coming with these two and also with the charge number densities, initial flux coming in the initial flux and target density are taken in the V power 4 in the numerator, written as the first factor. Let me write it in a compact way as dq over f times m square, where dq is the V power 4 factors cancel. So, there is a 2 pi power 4 and delta for P A plus P C minus P B minus P D and d 3 P B over 2 pi power 3 2 E B d 3 P D 2 pi power 3 2 E D. This essentially depends only on the momenta, which mean and the energy, mean 3 momentum and the energy or the 4 momentum. So, therefore, actually this is in some sense it is independent of the dynamics, it only looks at what are the kinematic variables. Okay. And the phase space factor is also included in this, and the flux, initial flux F is V A minus V C, the relative velocity between the two colliding particles, the magnitude of that 4 times E C E A. Let me first look at the flux factor F, which is equal to V A minus V C over 4 E A E C. Now, for a colliding beam, V A and V C are opposite to each other, and in that case V A minus V C is essentially sum of their magnitudes, or the magnitude of V A minus V C is V A plus V C, the magnitudes of individual these things, times 4 times E A E C. This is true when their angles are 180 degrees with each other, and then magnitudes can be just added. This difference is this the magnitudes, sum of the magnitude. Now, other thing to notice is that I can write P momentum, 3 momentum as E A V C V A. Okay, the relativistic momentum is written in this fashion. So, in that case I will be able to write this as P A over E A plus P C over E C for E A E C. Which is equal to 4 times P A E C plus P C E E A. Now, now we will go to a specific reference frame. Let me call the center of mass frame define it as the reference frame in which sum of the 3 momenta of the initial particles, initial states is equal to 0. So, here we have P C plus P A as the sum of the 3 momenta of the 2 initial particles, only 2 of them are there, which is equal to 0. This tells you that P C is equal to minus P A, and if we take the magnitude, I can write magnitude of P C is equal to magnitude of P A is equal to, let me denote it by P I. So, in that case F becomes 4 times magnitude of P A is P I E C plus magnitude of P C, which is again P I E A. I can take the P I out of the bracket, then it becomes E A plus E C. So, flux in the colliding case is basically 4 times the initial momentum, magnitude of the initial momentum times the sum of the initial energies. So, if I denote center of mass energy which means the total energy of the initial particles in the center of mass frame is equal to E A plus E C, which I denote as root S. We will see later on why we call it a root S, and in this notation we have the flux, initial flux as P 4 P I root square root of center of mass energy. Okay. So, we have sigma here, the differential cross section as dq over f m square, and f is what is given here in this thing. We will come to the factor dq. This is equal to 2 pi power 4 delta 4 P A plus P C minus P B minus P D Okay. So, now let us look at dq, which is 2 pi 4 delta 4 P A plus P C minus P B minus P D into d 3 P B over 2 pi 3 2 E B d 3 P D 2 pi power 3 2 E D. Firstly, there is a 2 pi power 4 factor in the numerator and then 2 pi power 6 factor in the denominator. So, altogether we have a 2 pi power 2 in the denominator, and let me split this delta function into delta energy E A plus E C minus E B minus E D, okay, into the other delta function, rest of it, which is a 3 dimensional d cube P A 3 vector P C minus P B minus P D all 3 vectors now. Then you have d 3 P D over 2 E D, and you have d 3 P B over 2 E B. Now, let us look at the this line here, second line here. So, that will give you P D equal to P A plus P C minus P B. This in the center of mass frame, which means P A plus P C is equal to 0, P D is equal to minus P B. Okay. And d q will be 1 over 2 pi power 4, 2 pi power 2 d 3 P B over 4 E B E D. I clubbed 1 over 2 E D with this, and you have a delta E energy function E A plus E C minus E B minus E D. Okay. The rest of the things are all taken care of. The other delta function and the other integration goes away, giving us this condition. All right. Now, let us look at this other integration d 3 P B. D P B, the 3 dimensional P B, let me write as P F the magnitude, sin theta cos phi in polar coordinate system, sin theta sin phi, where sin theta is the polar angle and phi is the azimuthal angle of PB and cos theta. In this case, D3 PB is essentially volume element here. When you vary the R component, the radial part or the PF, then you have a dPF, and when you change theta to d by d theta, then you have PF d theta, and for the azimuthal case you have P sin theta d phi. This is basically the similar to the normal volume element in r theta phi coordinates. Here we have Pf square dPf sin theta d theta d phi, and this is what you recognize as the solid angle or differential solid angle. So, this will give you then dq equal to 1 over 4 pi square. Let me write it in this fashion, 1 over 4 E B E D P f square d P f d omega delta E A plus E B. Let me write that as x minus E B minus E D. X is equal to E A plus E C, the initial energy, which is equal to root S, and it is by this delta function, it is also equal to E B plus E D. Let me do a little bit of manipulation here. I write x equal to E B plus E D. E B is m b square plus p magnitude of b, p b magnitude square under root, plus similarly m d square plus p d square under root. But we have P b equal to P f, which is also equal to P d as we saw. So, this is equal to, let me write it as m b square plus P f square power 1 over 2 plus m d square plus P f square power 1 over 2. Let me differentiate this as with respect to P f. That will give you P f over m b square plus P f square 1 over 2 plus P f m d square plus P f square 1 over 2. P f is common. So, this is essentially P f 1 over m b square plus P f square, that is equal to 1 over E b plus 1 over E d, which is equal to P f into E b plus E d divided by E b E d. Okay. Now, d q is 1 over 4 pi square P f square over 4 E b E d, right, and d P f dpf is now dx into E B E D over E B plus E D. Okay. This particular term is coming from dx by dpf is pf into ex. Okay, there is a pf factor. So, inverse of this is dpf by dx, okay, over pf. Now, this is and you also have the delta function x minus E b minus E d and d omega, of course. So, this is 1 over 16 pi square. A pf cancels with the other pf. So, you have a pf there. EBD, EBED cancels with the EBED there, and then there is an EB plus ED here. And let me take the d omega along with this, and you have the delta function d e delta x minus E b minus E d and integration over dx. Again, if you look at the last two factors, delta function and dx integration, you will see that you can integrate over dx now, this new variable that we have defined. So, this will give you, again, without bothering about the rest of the terms, factors coming with this, we can integrate this out because it is a delta function, and that will give you, integration will give you x equal to E b plus E d, since in fact, this is what we had used earlier. So, or E b plus E d is equal to x, we had taken it as root s. So, that will give you 1 over 16 pi square pf over root s d omega. It's as simple as that. And now, let us go back to the expression we had for the cross section. It is dq over f m square, and f is essentially 4 pi root s. And dq is 1 over 16 pi square pf over root s d omega. Putting these things together, we have d sigma equal to 1 over 16 pi square pf over root s d omega is essentially what the dq is, and you have 1 over 4 pi root s as the 1 over f factor, and you have the square of the invariant amplitude. This is equal to 1 over 64 pi square s p f over p I m square d omega, or I can write d sigma over d omega as 1 over 64 pi square s p f over p I m square. So, this is the differential cross section, and we will remember this, we will come back to this, but now we will give our attention to the m square, where m we had written as minus e u b bar gamma mu u a for the first current, minus g mu nu over q square, and which is the propagator factor, and then the second current u d bar gamma nu u c. We will see what we can do with this m, or taking the multiplying with the complex conjugate of the subject m bar m square. We will come to that in the next discussion.